Thank you, everyone, for joining us today. We are very excited to discuss the latest trends in the design of spacesuits. My name is Ellie Schmelzer, and I will be your host for this event. I'm a senior scientific project architect, and I work with clients within the aerospace and defense industries, mostly solving problems related to their research and development efforts. For those of you who are completely unfamiliar with PreScouter, we are a global research and innovation consulting firm. We serve clients in all of the major science and research fields. Before I introduce our speaker, as I mentioned, I would really like if everyone can keep muted until and unless they have a question or they want to participate in the presentation, which may very well be the case. We will be accepting questions throughout, and at the end, the speaker will be basically guiding you in terms of questions and allowing you to participate. Without further ado, I would like to introduce our key speaker, and she's Amy Ross from NASA. Everyone has already been very excited to hear her presentation. She is a spacesuit engineer with nearly 30 years of experience. And she has a quote that she shared with me that was really incredible, and it just showed how much she knows about spacesuits. She said that I've given a 2-hour talk about just spacesuit gloves. So that just summarizes it. The technologies that she's developing at the moment will be used in the spacesuits enabling humans to reach Mars, not only Moon, but Mars. So without further ado, here is Amy Ross, and I will stop sharing my screen.
Hello, and I will start sharing the screen here in a minute. Let's see. Yeah. Okay, so as Ellie said, I've been working on spacesuits, specifically the pressure garment, because there's 3 main components of a spacesuit. There's the pressure garment, the piece that's shaped like the human. There's the backpack that's on the back. We call it the portable life support system. And then there's also our avionics system, which is growing to include a lot of the scientific data recording equipment and communication sharing that we're going to need as we go explore deeper on planetary bodies. Okay. So I named my presentation human-shaped spacecraft. And let's talk about why I did that. So first of all, I'm going to ask you guys a question. What does a spacecraft do? What do you think of when you think somebody's going to live on a spacecraft, and what's that spacecraft doing for them? Any ideas? Oh, come on, the kindergartners have arms way up by now.
Well, we have a couple of things coming in the comments already. One is flying to the moon. Okay. Okay, so maneuverability might be a broad way of saying that. Other thoughts? Safety immediately comes to mind.
Safety? Okay. So along with safety might be staying alive. That's always a good one. Mm-hmm. Okay. And so let's talk about that in the framework of a spacesuit. So what does a spacesuit do versus what a spacecraft does? And honestly, they're largely the same thing. So the first thing that either one is to do is keep you alive, right? So it needs to provide the basics that you need to stay alive, which is pressure, oxygen, carbon dioxide removal, metabolic heat removal. So the basics of if I were to stuff you in a can and what do you need to stay alive, the spacesuit does that, right? A lot of that's the portable life support system at the base, but the pressure garment has a portion of those systems as well. Okay, and then there's the other things about the space environment that we also have to protect you from, to also keep you alive, sometimes less likely, but sometimes just as real and as routine a part of being out in a spacesuit or on a spacecraft, like the space station, for example. Thermal extremes. Every time the space station goes around the Earth in an hour and a half, it sees temperatures from, or can see temperatures from minus 250 degrees to plus 250 degrees. So that's a big thermal range, and that swings routinely every 45 minutes as the ship orbits. As you go out into deep space, you get some thermal extremes there as well. So that's something you have to deal with. Meteoroids and orbital debris, so hypervelocity impacts you have to worry about, and how do you protect against those. Radiation conditions, and then just the other things that could be, in the environment, especially when you're talking about space suits. You don't want sharp edges, anything that can puncture you, cut your suit, right? And then as we explore planetary surfaces, definitely the environment of the surface makes a difference, especially we think about the rocks and the sand and that kind of thing, the dust, when we're talking about environmental protection. So maneuverability, the space station, as large as it is, also does move. When we have some kind of impactor, either an old satellite that got in the way, or some kind of orbital body, like we've got meteors, big meteors that'll come through. We have to move the space station around more than I ever thought. I worked on the space station for about a year recently, and I had no idea how often we have to do those kinds of maneuvers to avoid things that might hit the space station. Also, the spacesuit does that to you, right? Does that for you. It allows you to move and go do productive work, which is a big piece of what I'm going to talk about today as well. So when you think about a spacesuit and a spacecraft in that sense, they're really a lot the same. Really, a spacesuit is a human-shaped spacecraft, okay? When you're thinking about building a spacesuit, and I've told this over and over again to new engineers as they join the team, there are two things you need to think about or need to know. One is, where are you going? So what environment are you going to be putting the system into? And then what are you doing? So what kind, in large, that means what kind of mobility do you require? Because for example, you say you're going on vacation. Well, that's nice, but you kind of need to know more before you're going to be able to pack properly, right? Are we going to the French Riviera, or are we going to Alaska in February? Are we going to do dog sledding, or are we going to go swimming in 80-degree water? What are we doing? Because you either are thinking about this, and maybe if you don't say this up front, somebody's thinking, I'm building sandcastles on vacation, and then somebody else is thinking, ooh, skiing and going to build a snowman. So you need to have that clear picture of where you're going and what you're doing in order to be able to design a spacesuit. That's what we basically call our requirements, okay? So we'll talk about three in general of many of those kinds of requirements. So mobility, dust, and sizing. Because I'm a pressure garment person, those are the kinds of things that I think about. If you were expecting to hear about life support technology and those kinds of technologies, that's going to be your portable life support people. And I know some about that, and I can answer a few basic questions, but I'm not going to be able to dive into those technologies. I think I sent to Ellie the fact that we have the International Conference on Environmental Systems. So it's ICES. So www.ices.space. And if you go there, our proceedings have a lot of other information in paper form in our proceedings about spacesuit technology as much as we're able to publish. Okay, so let's talk about mobility, though, because that's where I spend a lot of time. When you go to a planetary surface, the question, what you're going to be doing, is largely surface geology. That's the answer. Because we're there to understand more about where that body came from, how it evolved, and the way you do that is through the geological sciences. So a method to do that is to grab some geologists, start learning from them, and then also then put them in our spacesuits and ask them to do geology in a suit and see how that looks. One of the things we learned from the Apollo program, like in the picture on the left, was that a sample collection that a person on Earth would just go ahead and kneel down, grab soil sample, and be done with it. It takes two people to do that in suits. So that's good to understand. Then you can also see the subject, that's actually our geologist, Dean Epler, Dr. Dean Epler, who's a volcanologist. He is in the suit there and demonstrating, geologists are going to want to pick things up off the ground. They're going to want to get rocks and look at those rocks. And so having that mobility is really important to be able to do those kinds of tasks that a geologist typically is going to want to do. Okay? Because one thing I can tell you is that astronauts are very, very type A people, and they will push the tools you give them, including the suit, to the edge in order to accomplish their objectives. And sometimes they will do things like use their gloves as hammers, which is a really bad idea, just to get the job done, because they're very, very focused on getting the job done, and sometimes actually forget some of their own safety in that process. So you got to make the suit tougher than the astronaut's going to try to use it. Okay. The other thing you have to think about is interfaces, and I have this slide here on purpose because if you remember, when they went from Apollo 14 to 15, the big difference was they added the lunar rover. And the Apollo suit had to change because the pressure garment they had for the first lunar missions couldn't sit in a rover because of how it was designed. So they had to redesign the suit to allow that hip mobility so that people could sit in a rover. And so, you know, looking at those interfaces and making sure that your suit can do the jobs that those, those interfaces require, like sitting in a rover, as simple as that, is important as well. But the challenging thing is a lot of people don't think spacesuit every day. And so because they aren't thinking spacesuit every day, they don't think about what the impacts of having a suit does on your design. You can see the seats in the lunar rover look like big lawn chairs, and that they look that way because there's a suit there that has a PLIS, so the portable life support system, and so that makes you very, very deep as far as your seated depth. And so it looks like those seats are very long, but when you have a PLIS behind you, not so much, right? So those kinds of things then affect how your design works. So you can see the individual, it's a kind of a fuzzy picture, but in the middle bottom here, sitting in the seat, he actually doesn't have a back that he's sitting into because there's a big curved bar that goes behind him, because that's what the suit portable life support system will interface with. Okay, so those kinds of differences are some part of our value in helping other systems also design to the suit interface. Okay, okay, can you still hear me?
Loud and clear.
Yes. Yes.
Okay, I pushed page down. That didn't do it. Okay, good. So let's talk about what a planetary walking suit looks like. So I'm going to put you in a different kind of paradigm. Let's think about a scuba tank, okay? So a scuba tank is a pressure vessel that holds gas at around, I don't know, what, 800 PSI or something. And now we want to make it move. Does that sound like an easy chore? No, not in my head. But that's basically what we're doing with spacesuits. We have a pressure vessel that we are now asked to make it shaped like a human, make it endurable by a human, comfortable is another way to say that, and make it move like a human. I don't know about you, but I was a gymnast. I know that human bodies can do some pretty amazing things. So when you just sit down and think of it that way, it becomes a much more daunting task than you're like, oh, I'm going to make clothes that move like a human, and that when you come at it from spacesuits or clothes, it doesn't seem as big of a chore, a job, a challenge. But when you think of it as I'm building a pressure vessel that I have to make walk, it puts it in a different perspective, because that really is what we're doing. So it also helps you to understand why a lot of these features are here. I don't know if I have anything out. Page up, okay. If you look at the suit on the right here, one of the things you're going to see is that there's a lot of lines, what those lines actually are. So there's like 3 at the hip, there's 1 around the shoulder, right? There's actually a big one around the waist that's a little harder to see because there's a lot going on there. There's 1 at the wrist, which is kind of covered by the the over layer, and there's another one at the upper arm. And those are bearings. Those lines are the bearings, actually. And so those bearings are what allow the suit to rotate. Okay, if you think about a lot of your mobility, it's actually a rotation. You have a few single axis joints like your elbow, a hinge joint, and we can accomplish that through soft goods that you can see at the elbow and the knee here, and also at the ankle, for example. And the wrist is kind of a modified hinge joint like that. But when you want to walk, or you want to turn around and see what's going on behind you, those are rotations largely, if you want to do it anywhere near naturally. So in your suit, what you're going to see in this list on the left is a lot of different bearings, okay? Now, in between those bearings, we also have joints. Like, for example, from the shoulder bearing out to the upper arm bearing, we have a joint. It's a rolling external link rolling convolute joint, but that's what allows your shoulder to move up and down, like, you know, put your hand down to your side and move it up over your head. So that joint allows that mobility. Also at the waist, not only is rotation important, but flexion extension is, right? And so if you want to bend over and pick up a rock, not only do you need hip mobility, but waist flexion extension becomes really important. And so when you're talking about waist flexion extension, you got to sit in a chair and then like bow. That is your sit-up kind of mobility, right? And that's your waist flexion extension. Now, another mobility that you have is adduction and abduction. So you can move side to side, right? Like when you bend over to pick up a briefcase or something. Well, we've looked at doing that, but when you try to put these different joints, which take physical space, in a spacesuit, and you can see already here, we have our shoulder bearing comes down to like mid rib cage, and then we have our waist flexion extension and waist bearing joints that basically come down to our hip bone. There's not a lot of room there. So unless you have some extraordinarily long torsoed people, it's difficult to get each one of those ranges of motion incorporated physically into the suit architecture. Does that make sense to everybody? Okay.
Yes.
Okay. Yes. Thanks. I appreciate that. So, you know, we do sometimes have to make decisions about which type of mobility we need to include and what level of that mobility we need to include, because we are having to build physical joints into an external mobility architecture to go over a human to enable those joints, which are really included very efficiently in our body. For example, your shoulder joint or your hip joint, those ball and socket joints are really, really cool. And they do a lot for you that when you try to build it into a suit, gets really challenging, actually. Okay, so it's taken a long time to develop a mobility system that has a lot of the other requirements met as well. Because if you just want to optimize mobility, you can do that, but then you're probably leaving out some of the safety requirements, some of the leakage requirements, the other pressure retention requirements that you need. Okay, so it's like any integrated engineering system, it's very much a priority and a compromise game on your requirements. Okay, now when you talk about planetary suits, the boots also become very important. For the station, when you're doing a spacewalk or an extravehicular activity, EVA, the way you get around on space station because of the microgravity is using your hands. So the gloves became really important, and that's one of the reasons that we developed the current Phase 6 glove that had improved mobility from the previous generations of gloves. We got to largely ignore our boots for anything but staying in a foot restraint that held you in place while you worked with your upper body. But when you go to a planetary surface and you have a geologist, they walk a lot because the good stuff is never right in front of you. The good stuff is always, down the ditch and across the way. And so they need to be able to get to where they're going to find the samples that they want. Okay. And again, our spacecraft needs to provide that mobility. And so boots are key. If you've ever been hiking, you know how important a good hiking boot is. And you know how important the good fit of that hiking boot is, as well as other features like the the way it keeps out water or how thermally relevant it is to where you're going hiking, right? So you don't want big snow boots when you're doing a summer hike on the Appalachian Trail, but you do want those big snow boots when you're trying to climb Everest. So you got to take all those things into consideration and put that into the boot that you're going to need. Okay, I'm going to move on from here unless anybody has a question.
Amy, this is Glenn Johnson from Collins Aerospace. I have a question. That waist joint and the other joints, and they have to obviously articulate. Do you cycle test like we do in aerospace? And typically, what kind of cycles does that waist, for example, have to cope with?
Yeah, and another part of that too is, we use static seals as dynamic seals. So we have a lot of O-rings and lip seals that we have to use on rotating joints like that, because we still do need to, prevent leakage out of the suit as much as we can, because of the consumables worry, the logistics of it. So yes, we've been talking with, we have talked to our rotating machinery experts within NASA, and it's funny because when we talk to them, they're used to very, very high precision things that move very, very, very fast for hundreds and hundreds of thousands of cycles. And so when they look at our design, they're like, oh yeah, no, it's different than some of the machines that you might be talking about out of Collins, right?
Yeah, I'm thinking of undercarriage because there's a massive amount of, a lot of articulation and quite a lot of stress on, say, a 777 undercarriage.
Yeah. Yes. But we do, right? We do have to prove longevity of our design for the mission requirements, right? So if you go to Mars, you may be on Mars for 500 days. And so you need to prove with a safety factor that your suit can last with whatever maintenance cycle that you plan on it. So the only way to do that is to cycle. You can cycle at the component level, right? Just take the waist bearing and just cycle it. But what I was taught and what I've learned by experience is that the loads that you apply to the component will determine really the longevity that you have. For example, you can cycle that waist bearing, no problem, but you put somebody in a suit in a walking test and you're making that waist bearing with the loads, the dynamic loads of that walk, then you're going to see different wear. I mean, we literally have had to remachine a walking suit waist bearing following a long test because we wore it out. And so that was teaching us things about the stresses that we had on our ball bearings, the stresses that we had on our ball races, what kind of loads we were putting into the suit. And so, we learned a lot about very detailed design of a waist bearing from that cycling experience. So it's imperative and critical. Ideally, you'd like to have all the factors that could impact your longevity in that cycle test at the same time. So you want to be in a dust environment, in a low pressure environment, potentially with wind, with the chemical reactivity of the dust, and the temperature swings that you're going to see while you're walking in a suit. You can usually combine some of those, but maybe not all of those. So we do have to kind of test in bits and pieces sometimes and kind of put that information together as best we're able. That answer that question?
Yes, thank you very much.
Okay. But yes, cycle testing is important. And not just for the bearings, the soft goods too. Soft goods are actually harder to model and predict the durability of. And so I consider it to be critical that soft goods are cycled as well. Because you don't know how they're going to fail until you actually do that kind of work. Okay. So normally you see spacesuits in all their glory with their pretty white cover layer on them. And that cover layer isn't just for pretty, it is the environmental protection system largely. Okay, so it protects you against the cuts, the abrasions, the dust, the thermal extremes, those kinds of things. So you don't get to see what's underneath there. So let me show you, this is the current suit that we're flying. It's the shuttle, the Station Extravehicular Mobility Unit, EMU. And you can see here what the upper torso of that suit looks like. You can see a little bit of how the shoulder bearing is integrated into this suit. You can see how there's an interface here on the front for the module that allows control of the portable life support system, like turning the power on, turning the water flow on, those kinds of things. You can also see how we have the connection to the arm, to the glove, and that disconnect is there. Red is right, blue is left. So the crew members can keep it straight. And you can see there's an upper arm assembly and then a lower arm assembly here. So there's the two components, and there's a bearing in between those two. Okay. Over on the left, you can see the glove, and you can see it's a lot more involved than you ever would expect your hockey gloves, your ski gloves, your standard winter gloves to be, because there's a lot of work going on beneath the environmental protection to provide that mobility that we've been talking about. So if you don't build it in, it's not there. So you have to pay in space and weight a lot of times to include the mobility that you want. Okay. Okay, and so this is what you can get out of them. So this is on the KC-135, or the reduced gravity aircraft that flies sorry, it's Friday. It's been a long week. The parabolic flight path. And so that flight path, when you're coming down, can, depending on how steep you fall, like on a roller coaster, you can either be microgravity, or you can be 1/3 gravity like Mars, or you can be 1/6 gravity like the moon. So that was the one place that we could really test that gave us the actual gravity that you would be using the suit in. The downside of this test environment is that it's only good for like 23 to 35 seconds, depending on which gravity you've got. But you can still get up, you can still do some kneels, you can still do some, walking, running, and then we've got some, simulated rocks on the ground here, so it's not just the flat terrain, we've got some rough terrain. So you can kind of see that we can get idea of how well our mobility systems are performing, as well as over here on the right, you can see that's the Apollo suit in the back. So that's its kneel, that's the best it could do. Couldn't touch the ground in that posture, wasn't stable in that posture. Several times the technician in the back had to push them back up if they started to, lean and fall. Whereas the subject in our Mark III prototype in the front here, he was able to come down, touch the ground, stand back up, kneel again, touch the ground, stand back up several times within a parabola. And I'll tell you, the subject in our Mark III was a lot less tired at the end of the day than their subject in the Apollo suit. So I give the Apollo astronauts a lot of credit, because the tool we gave them did the job, and it did multiple jobs in the end for the mission to be successful. But when you're looking at a pressure garment designed solely for surface mobility, then you get a lot more out of it. Okay. And here's kind of the new standards of mobility that we're thinking about, like, can you sit with cross-legged in your suit? That seems a little crazy, but you can. And then, of course, astronauts always want to go further and do crazier things. And so this whole idea of belaying in a spacesuit, we haven't quite gotten brave enough to attempt, and we don't have enough experience to do so yet. But it's definitely a picture that has kept us working and striving to provide more and more mobility for the crew members. Another thing that makes us work at that is when you send an astronaut to Mars, I don't know if you saw The Martian, but it's true. They don't have help. They have to be able to do what they need to do on that surface, because you may not be able to respond to a question for 30 minutes, not to mention not being able to help them for, 6 months or better, with anybody else coming to see them. So they need to have as much capability as you can provide for them to be able to do what they need to do on the planetary surface. Okay. Now let's talk. Yeah.
One quick question in terms of the future mobility needs. This is Sofian Bukalfa with PreScouter. Have you ever thought about leveraging exoskeletons and adding them on top of a suit in order to enable those needs, or is that too complex to consider?
You asked one of my favorite questions. I'm not, now see, I get to talk from a spacesuit perspective. So in the end, there might be mission decisions that make that a more attractive option to me, because if you can't do the mission, what's the point of having a spacesuit? So if you need an exoskeleton and that's the only way you get it done, maybe. But the way my brain goes, because everybody likes it, everybody's seen the sci-fi, the way my brain goes is electronics fail, anything bendy like wires on a suit fail, it's additional mass that you're putting on a human. So there's ways to maybe manage that, but you have to think about the failure modes in case it does fail, because then how is a human operating if you don't have the exoskeleton, right? So until you answer those questions well, I don't tend to be a big fan of exoskeletons. Now, the folks, that being said, the robotics folks at JSC have, robotics has come a long way since I was, a little baby suit engineer, and developed my healthy dislike of them. So I have seen some work that they did, like with the GM glove and those kinds of things, where they did think some of those thoughts. So like, if it does go away, they had a glove assist that helped you open and close your hand, actually helped you close your hand, helped you hold your hand closed for grasping work. But we worked on that with the team for the suit glove. And so they actually had it where if it failed, you still had the glove mobility you expected, you just didn't have the assistance anymore, right? So you were still able to work if it failed. Now you still had that mass, you still had that extra stuff on the suit, right? Wires across bearings is a tough problem. So especially when that's a pressure sealed bearing. So, there's still things that make me concerned about the viability, the feasibility of making that a really useful tool. But maybe it's an exoskeleton you put on and you go do some heavy lifting and then you take it off. There's different ways that it could be included that might be really functional. So you don't have to take a backhoe and a forklift and things to the planet. You have an exoskeleton that the suited human can put on, do the heavy job, and then take off again to do their normal human mobility work. So I see the potential for it to get better and where I could get more happy about it, but to date, state of art hasn't convinced me yet. Now there's shape change materials, there's different things that could start to head you down that direction where it's going to get a lot more productive and helpful. Power is always a concern, right? So the power usage you have there is crazy. And so how do you manage that and make that work in your system? I can tell you just doing the basics of life support was challenging our power system on the exploration EMU that we developed. So, there's a lot of potential pluses, but there's a lot of practical minuses at this point. How's that?
No, thank you. Very, very insightful.
Okay. Yeah, so it's like anything else. The more you know about it, the more you appreciate it, but also the more challenges you see. So, okay, now we're going on to dust. Okay, so it's funny how people think about dust. We've been to the moon. We lived through it. Did we have some troubles? Did we have some comments about dust and dust management? Yes. But did we do the mission and come home alive? Yes. Some people in the world still think dust is going to kill you, like it's a snake reaching out to bite you as soon as you reach the surface. Other people are more pragmatic about it, but you have to face the fact that it is a real problem. Really, with a suit, I think it's a more achievable issue than the levels of protection that they want to provide to humans inside of the vehicle. And so I think we can get there, but how do you keep dust out of your house when you go inside and outside, right? I've got animals, a fair number of them. Dirt is a constant problem. They go outside, they bring dirt inside. And that's what our astronauts are going to do. So when you are trying to manage the dust, even if you are keeping the suit mostly outside on a suit port kind of concept, at some point you're going to have to bring that suit in and do maintenance. And so, how are you keeping the dust out of the habitable environment? And, in case you don't know, the lunar dust is basically like crushed glass. And so getting that into your lungs tends to be a bad thing. Okay. And we kind of don't know exactly what the Martian dust is going to do to you. We have some ideas, but again, it's probably not best to be breathing it in. So this is what those surfaces look like. Their dust is unavoidable. It is everywhere. It's like if you go to the beach, you will get sand in your belly button. It's just going to happen. Okay. And so, we learned this out in our field tests as well. You take the suit out, you have people work in the suit, and dust gets on the suit, and you just can't avoid it. I mean, you look at the boots in that middle picture, or the side picture, there's dust, right? Now, the good news from our field test, which wasn't we went for 2 weeks and would do maybe 2 runs a day over that time. We got dust, but not just tons and tons of dust like in our bearing races, which is one of the places you kind of want to keep the dust out of. The place we really haven't gotten to do a lot of work on even yet is understanding how the dust is going to impact your soft goods. One of the things we have been doing is working on what soft goods you want to incorporate to help mitigate the dust hazard, right? So the first thing is you don't have to worry about your dust in your bearings if you keep the dust out of your bearings as much as possible, right? But what materials are we going to use to do that? Because to date, we've been using materials that have a weave, and so the dust can penetrate the holes in the weave. Okay? Like so. So, I'm going to talk about Martian dust because we've done some work there, and we have a really exciting thing that we've got in work. But if you look at this exploded or microscopic vision of the soft good, you can see that weave there, and you can see how the dust is just getting in through those different holes in that weave. Okay. You can also see how the dust can accumulate on a rover, for example, and then not be there because the wind will come through. The force of the wind is low because it's not dense air, but still the wind is blowing and moving those particles around. Okay, and so you have to think about dust. How are you going to deal with dust? Another trick of the Martian dust is that it is chemically reactive. So when you expose Martian dust to water and oxygen, which is what leaks out of a spacesuit, it forms perchlorates or perchloric acids. I'm sorry, I'm trying to remember. And that is not good. And so we don't think it's a real strong acid, but when we tested some suit materials with it, and it doesn't seem to be too bad as far as reactivity with our materials, but you definitely don't want it in the suit, because if you've got soot in your habitat, then you're going to get dust in your habitat, then you're going to probably get dust in your suit, and you don't want to have that being breathed in by the humans either. Okay, and then of course particles can jam mechanisms. Like I said, your bearings is a really good example, but there's other mechanisms on the suit that matter as well, like your umbilicals that get you tied back to the spaceship with oxygen and water for cooling and those kinds of things. And then we don't, like I said, we don't understand how those particles are going to increase the wear of the suit. So that's something we really need to spend more time on, in my opinion. Okay, so one of the things that we are doing for that, and this is really exciting to me because I may not get to build a suit that goes to Mars, but dang it, I got some spacesuit materials there. This thing that you're looking at is really kind of about this size, and it is the calibration target on the Sherlock instrument on the Perseverance rover that's on Mars now. And so the bottom row is our spacesuit materials. So the leftmost is our helmet material, and the others are other samples of spacesuit material on the suit, and one of which has a dust-resistant coating on it. Okay, so here's those materials: the polycarbonate, Vectran, orthofabric, Teflon, and then the coated Teflon with the dust-resistant coating. Okay. And so fortunately, the folks who were working on the Sherlock instrument, there was part of that team here at Johnson Space Center, and some of the folks who were working on it were geologists, because that's what Sherlock is helping with. And they know that we're working on the suits, and they need to do geology in the suits. And so they said, hey, what about doing this kind of thing? My mentor had been trying to do this job since I started at Johnson Space Center, getting spacesuit materials on Mars for a materials exposure experiment. And so I'm just really, really excited that I got to do this. And so again, you can see the materials here. And also underneath our polycarbonate, we had that geocache coin, which was really cool, which is a 221B Baker Street, which is, Sherlock Holmes, if anybody's a fan. And then, which I am, and then our NGMAT coating, which we did through our Small Business Innovative Research work, came in on that Teflon material in the end. Okay. And there you can see the calibration target on the Perseverance rover on Sherlock instrument. And there you can see it again right in the middle of the picture here. So very cool. And it's now on Mars. Now the idea is that we're going to take, using the Sherlock spectrometer, we're going to take images that will give us a profile of the spectrum coming off of it, and we're going to be able to do ground testing that will simulate the exposure to the radiation on Mars, and we'll understand how the Mars environment is different from our testing and how quickly these materials degrade over time, based primarily on the radiation exposure, but also the dust will be a part of that. Okay, and we'll see how, so from the images, how well that dust-resistant coating is protecting the material as well. Okay. Okay, so there it is. In all its little glory. Now, when you talk about dust, as I was saying at the beginning, it's not just a suit problem, right? You have to manage dust across the entire system of your mission, right? So from your habitat design, your spacecraft design, your suit design, all those things need to play a part in minimizing dust in your habitat, okay? And inside your suit, actually, too, your suit loop as well, which is another habitable volume, right? You don't want people breathing dust in the end. And so having kind of a mud room idea is one. There's this, it's not bad that it's here, but I don't tend to like it either. It says incorporate dust repellent technologies into suit outer layers, and that's the picture on the top there. Again, wires, electricity, power. I'm not excited about that being in a suit, but there's other places you could use that, right? So it's not a bad technology. It's just maybe not the best plan for the suit. And then, of course, keeping your suit maintenance area, like we talked about at the beginning again, is another strategy to help keep the dust and habitable volume down. Okay. Okay. Any questions on dust before I move on to sizing?
I have a question, actually.
Yep.
My name is Marianne. I'm with PreScouter. It's not specifically related to dust, but I have a question more in terms of the inside out leader. So talking about space contamination with microbes, for example, from Earth or human contamination. I'm not sure if you have any slides later on that, but I was thinking, how well is space contamination taken into account in the design of the spacesuits, and what are the precautions that are taken at this moment, and how do they change with the complexity, with all those angles and joints in the spacesuits?
Yeah. So we have come to an agreement with the scientists. At least I think we've communicated well, so they understand our situation. And I think they're accommodating for that. So planetary protection, it goes both ways, but we're talking about contaminating the planets we go to, is what I hear in the question. And basically, we will contaminate the planet we go to. Wherever you have a suit doing work, we will contaminate. So there's different ways you can handle that. One, don't let humans go where you really want to protect some of the potential, evidence for life, those kinds of things. So there is a strategy by the planetary scientists community to just like cordon off various areas that say, hey, we want to save this for later evaluation, non-human, maybe robotic or however else, or once we get smarter about how we do our human exploration. And we're just not going to go there. Now, there's some trouble with that, right? Once it gets in the environment, it kind of can move around. There's wind on Mars, and but that's why the other strategy of thinking about, we need to be able to, characterize what we bring better so that we can understand if what we find is just us or something that's indigenous, right? So the bottom line is we will contaminate. You can't stop that. You can't make a leak-proof suit. Not doable. Not realistic. Now there's things we could do to help manage how much gets out, right? So there's things we could do at our bearing, maybe inlets and outlets of our flow. Now, I'm making it sound like we intend to leak. We don't. We try to not leak, but you will leak some. I mean, it's not a lot, 100 skim or something, but you will leak. So there's things that we could do where we can try to, put some treatments or filters or something that catches or kills anything that we let loose, right? So that's another thing we have been talking about. Okay.
Thank you. That's very interesting. I actually worked with extremophiles and astrobiology at my PhD, so that's why I had the question, but very interesting. Thank you.
Yeah, no, those guys are very cool. You can't kill them.
Amy,
Okay.
Amy, could I ask another question before we go off that topic, because that's quite a large structure. So my background is aerospace and stuff flying, and I can imagine what military aircraft weight kind of costs and what commercial aircraft weight. And I understand space is an order of magnitude different. So what is the focus on weight in all the things that you do here? And it must be astonishing to focus on weight.
It is. And so that was one of the things I actually had to educate our EVA office management about not too long ago, just a few years ago. They were asking for more mobility, but they were also asking for less weight. And so one of their options for getting less weight was to remove bearings. And so we had to have that conversation about bearings are mobility. So if you can't have both of those things you just asked for by removing bearings, okay? So we had to have that discussion about there's money you could spend to optimize your bearing mass, right? To skinny them down to where they're still structurally sound, but they're as light as they can be while being structurally sound. And that just takes time and money. It's just engineering. But you got to pay for that time and effort. So that was one of the things we could do to offer to reduce those. You can be really slick about how you integrate the bearings to the rest of the soft goods. We've looked at that several times. If you want to be able to remove your hard goods from your soft goods, which typically you want to do because the soft goods will wear out long before your metal components will, you typically want to have some kind of clamp or bolt or screw interface. And that's where some of the weight is. So if you are willing to throw out the entire suit when your soft goods wear out, you could save some mass there. You can also, is it really taken, this is where we're very different from the Russians, right? This is where you get the pencil out, sharpen it up, and you go to town. Because there's a lot of detailed engineering where you can do mass reduction. The materials you use, like picking titanium or beryllium versus stainless, sometimes stainless is still a right answer, but you got to take that mass hit, so you got to understand why you're using the materials you're using. You can talk about functionality you want to give up, because usually when you do give up some functionality, like if you want to have a suit that only lasts for 6 hours versus 8 hours, really you got to go more like 3 or 4 hours versus 8 hours. Then you can lose some mass, and then you can invest in, but probably also buy some mass on a recharge system or that kind of thing. So you got to be real careful when you're doing a subsystem trade versus the system trade, right? Because you can make a judgment that's good for the mass of the subsystem that doesn't make the whole entire system happy. Like the vehicle gets heavier because you're now only have a 4-hour EVA suit, right? I mean, that doesn't necessarily make everybody happy.
Hi, Amy. Sorry. We're really running out of time.
Oh, okay. Yeah, sorry, I'm not on the clock.
Yeah.
Okay, yeah, we are. So let me just go into sizing real quick. Fit is different than sizing. I can get into any suit that you want me to, as long as it's, I'm not physically just too big for it. And so I have, like our Mark III suit is made for a 6-foot plus person, and I can get in it and move. But do I fit? No. And so so defining what good fit is a tricky business, because humans are all shaped very differently. So even when you say somebody is small, maybe the percentage of their their percentile for a certain dimension isn't small. Like here on test subject 2, you can see there's biacromial, which is your shoulder, kind of basically that little point on your shoulder is your acromion. So if you go between those two across your shoulders, I'm a 6%, that's me, sorry. And then if you come down here to the hip breadth, I'm hippie. So, you know, I'm 5'4", so I'm not real tall, but I'm also not real broad in the shoulders, but I'm hippie, you know, so, and I've got a big bicep, there you go. So there, you know, people are funny shaped, basically it comes down to. So when you're looking at different size people, you got to be real careful, because when you say small, they may only be small in one certain dimension, okay, and not all the way around. Why isn't my page down going? There we go, back on this. For example, on the right here, you've got a person who's shorter who has a longer arm span, right? So there you go. And we just gave, you know, our large person there for scale. He's about 6 foot. And then you got to, you know, this matters because you got to figure out where to put those controls on the front of the suit. And so you can see what the current suit's display and control module, DCM, looks like on the humans. So you can see where our larger, broader folks have less of an issue or impact on their mobility than, say, like this person in the middle or on the end on the left, because now that piece of equipment is basically in their way for their mobility. Okay, hands the same thing, right? You're going to have hands that are basically the same length, and then the circumferences are very, very different. So what it comes down to is I can build a suit of any size and shape. People will say, why don't you build small suits? Well, dang it, I'm 5'4". I'd love to build small suits. Building them small isn't a capability issue. Building them small is a money issue, and it's been a practicality of which we get like one pressure garment prototype every 10 years kind of thing in our history. It's been better recently, but you know, in general, when I get one, I have to make it last, and I need to be able to put a lot of different people in it. So getting it big makes sense. But when you are looking at building for flight, building one small, like we did here with the, this is the Z25 suit with EMU shuttle station EMU pants on it. Then it makes sense because you're trying to get all those systems and interfaces into that smaller volume. So then that makes a lot of sense for engineering purposes to build a small one. Plus, then you get to stick half of your population into it that doesn't normally fit into the big suit very well. Okay, and you know where you're going and what you're doing, along with sizing. You know, you can see a variety of shaped people, a variety of different suit types here, because it's suit design depends on what you're doing and where you're going. So I'm sorry to have to fly through that bit and not leave a whole lot of time for questions here, maybe not much at all. I'm happy to stick around for a few minutes if somebody wants to stay and answer questions, if that's allowed. But that just gives you an idea of how I can talk for 2 hours on gloves. We talked about three little requirements, really. Okay, but we can do things like this. So this is a doable thing, and you do have to make some compromises, but we can make suits that allow people to explore planets.
Thank you so much. This has been absolutely fascinating and very informative. And yeah, we should have done this and allocated maybe 2 hours. So, but if anyone has a last quick question, we can take 1 or 2 more really quickly, and then we will wrap up and thank our speaker. And you can just go ahead if you have a question and unmute yourself.
This might be a longer question, but just looking at some of those earlier partners you presented, I'm curious, how do you typically collaborate with startups and academics, and how does that innovation process at NASA work?
Yeah, our world is changing around us, as you're probably aware. So that's changing as we go. There are several different avenues. The Small Business and Innovative Research, there's also the STTR, and I forget what exactly that stands for, but it's got an academic component to it. So we have a call each year for proposals to different technical areas on different problems within those areas, and people can apply for funding. Gosh, I can't remember what SBIR's limit is to start. It's like $100K or something for like a 6-month period. So basically we give you some money to do some basic technology development. It's usually the lower end, if you're familiar with the technology readiness level scale. If not, go look up NASA TRL on Google. But it goes from 0, which is just an idea, to 10 or 9. It's a flying space system, right? So usually those are down in the 1, 2, 3, maybe 4 level, where, hey, I've got this thought, I've got this little baby idea, I want to try to show you that it could work, right? So that's one way. We do have offices here at Johnson Space Center and the other centers, NASA centers, that you can contact to say, hey, I'm trying to solve this particular technical problem. Is there somebody I can talk to, right? So there's ways to do that. We also have the university side of that. So we reach out to universities routinely and are trying to partner there better. Even now I saw a bunch of jobs where you could be a part-time person whose your job was to interact with Rice University, University of Texas, Texas Tech, those kinds of things. So I can, if you want to send me something specific, I could probably help you maybe get pointed in the right direction for that kind of interaction. But our business office, and then we have organizations that are also looking to partner up with companies and just academia. So
thank you so much.
Fantastic. Thank you.
Yep.
Okay, last opportunity for something really quickly.
Can I ask a very quick one again, or does somebody else have a question?
Can I?
Yeah, that's someone else.
Hi, I just want to know what you thought about the Tesla spacesuits.
So SpaceX?
Yep.
Yeah. So let me show you this picture again. There are different kinds of spacesuits. So typically I've worked on, although I have done some work on the others, I've worked on EVA suits, right? Extravehicular activity suits. Those suits are always pressurized when you go outside to do work outside of your vehicle. They are very different from, say, this orange one here or the white one on the right. Those are crew survival suits. You wear them when you launch or land or other dynamic phases of flight when you might lose cabin pressure. That's the kind of suit that SpaceX has today. It is basically a human-shaped bag that holds pressure in when you lose cabin pressure. So you do not go unconscious and you do not hopefully die, right? That's it. The basic idea of it. Obviously, you can expand its requirements beyond. So like over here on the advanced crew survival suit, the orange suit, it has a life preserver unit on it. It carries a parachute a lot of the time. It has emergency water. It has, emergency med kit. There's a bunch of other things it has involved in it, like a high altitude Air Force flight suit or Navy flight suit. So that's what they have, and theirs is, I think, stripped down to do the basic. We're going to provide pressure and oxygen to the humans so they don't die in case of loss of pressure, cabin pressure. They had a requirement to make it look badass. We don't get to have those requirements. Our requirements are all very, very, very functional, and usually to a high level of reliability. So your requirement sets allows you to do different things, and they have a slightly different requirement set.
All right, we'll allow Glenn Johnson to ask his question since he tried doing that, and then that will be the last question for the program today.
I just like the badass comment, Amy. That was a very good. Your suits have to protect you as a real space station. Anyway, there doesn't seem to be much in terms of composites in that waist joint or in the actual O-ring joints and the seals. Is there a historic reason that you stayed away from composite parts? Do you not trust them at the pressures?
So we have kick loads, impact loads, and a lot of times we've had challenges making those composites meet those. Also, although the NDE, non-destructive evaluations, are getting better, trying to make sure you have a solid structure over the life of the structure is more complicated with the composites. That being said, we are looking at them, right? We're looking at them, we're looking at plastics, we're looking at carbon fiber plastic composite. We're doing a bunch of different things, but we just haven't been able to spend the materials development money to get any of those new materials that we think have the performance we want to where we can include them in a suit yet.
Okay.
Great. Thank you so much, Amy. This was really fantastic. And we will just distribute the recording to anyone that is interested. And thank you. And I hope you have a good day. And maybe we will collaborate on some topics in the future.
Sounds good. Yeah, I hope you got your questions answered. Hope you enjoyed it. And thank you for having me.
It was fantastic. Thank you very much. Bye. Have a good day. Thank you.
Bye.